Inside our power plants, massive synchronous generators spin continuously, converting steady mechanical rotation into the balanced electrical load that powers the grid. But that balance is fragile. If a tree falls across the lines, it creates a three-phase short circuit. Instantly, system resistance drops to near zero. Electricity seeks this frictionless path immediately, resulting in an explosive energy release capable of incinerating the surrounding infrastructure. It's common to think of a short circuit as a broken dam, a single, unchanging flood of electricity that pours forward at a constant rate until the source is cut. In reality, a fault current is a dynamic, shape-shifting entity. Treating it as a constant value would cause every safety device on the grid to fail during the surge. To survive a fault, engineers have to slow down time and track how the generator's electrical output physically mutates, millisecond by millisecond. If we freeze time exactly at the moment of the strike, we enter the first and most violent phase, the subtransient stage. In alternating current, the equivalent of resistance is known as reactance. At the very beginning of a fault, the generator's effective reactance is at its absolute lowest point. Lacking resistance, the initial current spikes to astronomical maximums, shown by the extreme height of the first peak. A DC offset also pushes the wave off-center. The dotted envelope lines reveal this asymmetry forces the current to cycle on one side, multiplying its destructive power. This initial 50 millisecond window represents the moment of maximum electromechanical stress, a force capable of ripping heavy bus bars right out of their mounts. As we move past those first few cycles, the fault transitions into the transient stage. The massive current draw depletes the generator's internal magnetic flux. As this field distorts, the machine's internal reactance rises. Consequently, the overall size of the electrical wave shrinks. Simultaneously, the off-center DC offset decays, pulling the waveform safely back toward the horizontal axis. The current remains deadly, but the shifting magnetic environment is actively choking off the extreme spikes, buying safety systems the time they need to operate. Beyond 500 milliseconds, the transient chaos ends and the system enters the steady-state stage. The generator has now reached its stabilized condition, operating at its highest state of internal resistance, known as synchronous reactance. The resulting output is now a much smaller, perfectly symmetrical, and endlessly repeating rhythm, seen here on the far right of the waveform plot. Induction generators, like these turbines, would see their fault current simply collapse to zero because they lose their external magnetic excitation during the strike. But a synchronous grid generator is different. It continues to pump this steady-state fault current indefinitely until it is physically disconnected from the network. This creates the ultimate engineering challenge. How do you design a mechanical switch to safely break this massive flow of energy? Attempting to open a circuit breaker during the subtransient peak would be catastrophic. The electrical pressure is so high, it would create an arc that would instantly vaporize the metal contacts. Engineering the solution requires patience. Protection relays are designed with a minimum time delay, intentionally waiting for the most violent part of the subtransient surge to pass. The system specifically waits for the transient decay to reduce the current down to a survivable threshold. This value is known as the symmetrical breaking current. As the mechanical contacts pull apart, they stretch and cool the electrical arc, successfully extinguishing the energy in a controlled environment. Grid stability rests on this precise timing, a millisecond by millisecond synchronization with the electromagnetic forces that determine when a catastrophic explosion becomes a controlled break.